How's it going, everyone? This is going to be a walkthrough of a hypothesis testing question where we are looking at a comparison between two different samples, two independent samples, and a claim made about the difference between their population mean values. So we have a company claiming that their prices are lower than their competitor for a particular type of product. A study shows that the company has an average price of $245 with a standard deviation of 30, while the competitor has an average price of $250 with a standard deviation of 42. And this study looked at 20 items belonging to the company and 25 items belonging to the competitor. Now we want to test the company's claim using a significance level of 0.01. or 1%. Now, in these kinds of questions, when we're looking at two independent samples, there's a lot of information given, and it's easier to write it down. So let's call it the company, and that will be our group 1, and the competitor, and we will call that group 2. And for each of these groups, we have a sample size, a sample mean, and a sample standard deviation. So for the company, 20 items were looked at based on this paragraph here. The sample mean was 245, and the standard deviation was 30. For the competitor, 25 items were looked at, that's our sample size, with a sample mean of 250 and a standard deviation of 42. So we're going to be coming back to these values. Now what the company claims is that their prices are lower. Okay, so what they're saying is that the mean value for group 1 is less than the mean value for group 2. And another way we can write that is we could say the mean value for group 1 minus the mean value for group 2 is less than 0. Just taking mu2, moving it to the other side of the inequality, right? If mu1 is smaller, well then we have a small value minus a big value, the result is going to be negative. The result is going to be less than 0. So two different ways of writing the same thing. And either way, this is an alternative hypothesis because there's no equals here, right? There's no possibility of equality. The null hypothesis, which will be contrary to that, will be that mu1 is greater than or equal to mu2. Or alternatively, mu1 minus mu2 is greater than or equal to 0. So it has that possibility of what mu1 minus mu2 might be equal to. And the claim here corresponds to H1. So that's step 1, writing down our null and alternative hypotheses and the claim. Step 2 is finding the critical values. Now, if we look at this form of our alternative hypothesis, we see that the difference has to be sufficiently less than 0. So there's only one way we can reject our null hypothesis and go with an alternative, and that's with a value sufficiently small. So we have a one-tailed test, and it's going to be a negative tail because we need a sufficiently small test static to reject our null hypothesis. So our entire alpha, 0.01, is going to be in that tail right there. And we want to find our critical value. So our degrees of freedom. Now, how degrees of freedom is calculated differs depending on what course you're in or what organization you're working for, what the application is. For the purposes of this walkthrough, we're just going to use the smaller of the two sample sizes minus 1. Our sample sizes are 20 and 25. So we're going to take the minimum value of n1 minus 1 and n2 minus 1. In other words, the minimum value of 20 minus 1 and 25 minus 1. So whatever's smaller between 19 and 24, and that turns out to be 19. So we just took our two sample sizes. Whatever the smaller one is, subtract 1 from it. That's how we got our degrees of freedom. So we're going to go to our t-table. We'll look for 19 degrees of freedom and a tail size of 0.01. So there's our t-table. Our tail size of 0.01 is right here. We find our one tail size on that top row. And then we scroll down, match it up with our degrees of freedom in our leftmost column. There's 19 degrees of freedom. And so we have 2.539. That's our critical t-value, 2.539. Now the table only always gives us the positive t-value. It's up to us to know that it should be a negative 2.539 because we have a negative tail. So negative 2.539. Now we want to calculate in our step 3 our test static to see does it reach negative 2.539 or not. Now, the test static for two independent samples is the difference between your sample means minus the hypothesized difference between your population means divided by, now what you're going to divide by differs based on your assumptions about the standard deviations or the variances. For the purposes of this walkthrough, we're not going to assume that our population standard deviations are equal for these two groups. And we're going to write our test static like this. Standard deviation of group 1 squared over the sample size for group 1 plus the standard deviation of group 2 squared over the sample size for group 2. Depending on what course you're taking, you might have to look at certain assumptions made about the standard deviations, the population standard deviations about the two groups in order to determine what the test static is. But if you're taking a course where it's just this is always the test static used, well then this is always the test static used for two independent samples. So then we just plug in the numbers. So x bar 1 was 245 and x bar 2 was 250. So we have 245 minus 250. As for the hypothesized difference between our population means, well, as per our null hypothesis, we're setting that equal to 0. So minus 0. Then we have the square root of the standard deviation squared divided by the sample sizes. So we're going to have 30 squared divided by 20 plus 42 squared divided by 25. So 30 squared divided by 20 plus 42 squared divided by 25. And then we just calculate what this comes to. So 245 minus 250 is negative 5. Minus 0, it's still negative 5. Then we have 30 squared divided by 20 plus 42 squared divided by 25, that comes to, under the root, we have 115.56. And the square root of that is approximately 10.750. So, negative 5 divided by that gives us negative 0.465. Negative 0.465. Now, if we were to plot that on our t-scale, negative 0.465, well, it's 0 in the middle. Negative 0.465 would be somewhere there. It's negative, but it certainly does not reach negative 2.539. So, we did not reach our critical t-value, so we are not rejecting our null hypothesis. So, our step 4 is that H0 is not rejected. And what does that say about our claim? Well, our claim was attached to the alternative hypothesis. If we're not rejecting H0, if we're sticking with it, well, then we're not going to the alternative hypothesis, so we're not going to the claim. The data does not support the claim. So the claim is not supported. Now, if you prefer the p-value method, you would have to look for 0.465 on the t-table, right? The t-table only shows the positive values, so you would have to look for positive 0.465 at 19 degrees of freedom. Now, if we look for positive 0.465, you'll see that, well, we never even get there, right? 0.465 is even more to the right of the smallest number here, because the numbers get smaller as you move to the right. So if we look at what p-value that corresponds to, it would be even bigger than 0.1, right? Because your probabilities here, your tail sizes, get larger as you move to the right. So we have a p-value greater than 0.1, which is certainly greater than 0.01, which is our alpha. So p is greater than alpha, which again means you do not reject the null hypothesis. The same conclusion that we came to here. So that is how you do those kinds of questions. I hope that helps, and until next time.